little bit over the project. So we are working on the Open Catalyst project, and our mission statement was using AI to model and discover new catalysts to address the energy challenges posed by climate change. And the project was started to find scalable and cost-effective solutions to renewable energy storage. But we have a challenge, which is searching for cost-effective catalysts to convert renewable energy to other fuels at a quick rate. And our solution that we are trying to approach in this project is trying 3 different neural network architectures to approximate density functional theory, which I'll explain a bit more. So density functional theory is a quantum mechanical simulation, and it's often used to compute interactions of atoms using this process called relaxation. And it's basically just this iterative process to combine different locations of atomic nuclei and predict the energy of the system. And an advantage is that we can understand the efficiency of the reaction because we can figure out how much energy results from or is needed to drive the reaction. But one of the main disadvantages, and the one that we're trying to overcome, is that DFT is very expensive and takes a long time. It usually takes around hours or days per relaxation and scales with the number of electrons in the system.
So throughout this project, our goal is to understand the complexity of the system model published on the Open Catalyst project. From there, we can use some machine learning libraries such as PyTorch to optimize the to improve the performance of the model. If the model performs well, it will lower the computational cost of the new material discovery process, which currently depend heavily on the density functional theory. With that being said, one outcome we have to achieve is decreasing the error in the energy prediction of the current model. To do so, we need to find better feature engineering. Furthermore, we hope that the modified code will have better runtime performance.
Yeah, so our data is part of the data set we use is provided by the Open Catalyst project. And overall, it contains 1.2 million molecular relaxations, as well as 250 million DFT calculations that models can train and learn from. But since our models that we work with only focus on predicting energy and forces, we only use the DFT calculation part of the data set, so the 250 million part. So there are varying sizes of this data set, ranging from 200K, 2 million, 20 million, and 250 million. But we trained our models on the 200K size data set for a few days at a time. And this was enough to be able to identify any trends that we saw in our results that our model had. This data set is unique from other data sets that train on DFT calculations because it contains both inorganic as well as organic molecules and compounds.
So here we will discuss our features and our models that we used. So like mentioned before, we're testing 3 types of models. We're testing CGCNN, testing SCHNET, and DimeNet. So crystal graph convolutional neural networks, or CGCNN, is a framework for representing crystal systems that provide both material properties and property predictions. The crystal structure by the crystal graph encodes both atomic information and bonding interaction between the atoms, so it can help us predict these properties. Second, we have SCHNET, which is a continuous filter convolutional neural network, and it's used more for modeling quantum interaction as opposed to CGCNN, and it's better for obtaining more differentiable energy surfaces. Third, we have DimeNet, or directional message passing neural network, and it's a graph neural network that integrates directional message passing and incorporates atom permutations, translations, rotations, all different kinds of everything. We also work with a variant called DimeNet++, which is an improved version of that model that is computational, cheaper to implement, and more accurate. So we use multiple features as seen in the table in the bottom. These features consist of common attributes of atoms like electronegativity, then atom size, and these help in the prediction we would like to make. So we use 2 main types of features. There's K-hot and continuous, and these play a huge role in how our predictive capabilities work, as well as hyperparameters such as cutoff that tell how the model, how radially far away from one atom we want to compute things. So from this, we came to a few initial conclusions that DimeNet has the best overall performance in predicting atomic forces and energy. And then next slide, we'll talk about our results.
So here are 3 important performance metrics that we need for analyzing our machine learning models, which are energy, mean average error, the energy forces within threshold, and the loss. So as Jay talked about before, the DimeNet framework outperforms both the SNET and CGCNN framework in all these metrics. And following these results, there are several decisions that we need to make. And those would be whether we implement either the K-HOT or continuous embeddings, and whether we continue to optimize all three of our frameworks, taking a multiple model approach, or if we pivot to optimizing our best performing algorithm, namely DimeNet. Regardless of all of these decisions, we have to continue our work with feature engineering and beginning the process of hyperparameter tuning, architectural optimizations, and using alternative iterative methods for numerical optimizations. When these optimizations are made, we will use these to deploy it on our larger OCP dataset, whether we use just a single model approach or a best performing model approach or a multiple model approach. Now, all of this work that we've done in the short term has significant long-term impact, as not only would we have found a computationally efficient and effective model to find electrocatalysts to store renewable energy, but this was also effectively address the energy issues posed today by climate change in a cost-effective and efficient manner.
That's the end of the presentation. Okay, so we have about a minute and a half for Q&A. Do we have any questions from the audience? I guess I'll ask a question. So looking back on this project, what do you think is the one learning you achieved from this project? How does it differ from like any other data science projects you did?
Yeah, I think one thing is that in data science projects we learn in school, at least like in the lower div classes, we've been taught to work with feature engineering, but rarely have we ever had to like dive deep into the code and understand exactly what the code is doing. So I think for this project, we were each assigned like a certain model to study up and understand really well. So and it was from like a really large code base. So I think this project really helped us like be able to dive deep into the code and understand exactly what how all the code works together.
Awesome. That's all the time we have, and really amazing work and really high impact type of projects. The next project would be Goodly Labs. You can take it away. Do we have Goodly Labs here? Okay.
Yeah. Can I share my screen?
Yeah. Do you have permission or no?
It says it's disabled.
Is there anyone else on the team that is granted the permission? How about?
Did Andy make it into the breakout room? I think we lost a person in the.
Okay, so how do you feel about being the third team after HireB while I sort this out with Arlo?
That sounds good. That works for us, I think.
So HireB, are you ready for this?
Sure, I think we can go.
Awesome.
I will share my screen. All right, good afternoon, everyone. So our project is about job and resume matching using natural language processing. So I guess we can do a quick introduction of ourselves first. My name is Sunny. I'm a junior studying data science and economics.
I'm Varen. I'm a second year studying computer science and applied math.
I'm Andrew. I'm a second year studying ETS and math.
Yeah, and our supervisors are Louisa and Bahit. I believe Louisa is also here today. And so basically a quick background about the company. So
HireB is deep tech startup building future-proof hiring solution for small and medium business globally. And basically the problem that we are trying to solve is that COVID-19 created a lot of disruption for organizations, and employers are now facing increased levels of uncertainty affecting every aspect of human capital management market. So there is an urge to create a scale technology tackling the change priorities of those workforce, and that is noticeably emerging. And the goal of our project is to experiment with different machine learning or natural language processing algorithms that are used to match resume and job vacancies and vice versa based on candidate skills, background, previous hiring decisions, and a number of other parameters. So after we researched a lot of algorithms available, we ended up building our model based on three algorithms. And I will present the first one, which is word embeddings. And more specifically, we use word-to-vec model. And essentially, word-to-vec is using vector representation of words. So in that case, words that occur in similar contexts will tend to be closer in the vector space. So on the right-hand side, there's a graph that you can see, and this is a two-dimensional projection of embeddings. And you can see that the words with similar meaning tend to be clustered together. So that's essentially the concept of word embeddings. And basically, we trained a word-to-vec model on 3.4 million job postings on Indeed in 2020. And then we convert documents, which are job descriptions or resume, into vectors and find the document similarities between job description and resume to rank the applicants of specific jobs. And now I will pass on to Andrew to talk about LDA.
Yeah, so for LDA, the idea of LDA model is that we treat documents as a bag of words model. So each word is represented by a unique number as an index. And then we train the model on a large data set of job descriptions to train the model to recognize common topics. And in order to optimize this model, since the LDA model can have any number of topics we want, we optimize the number of topics by using coherence scores. And then once we have this model, we were able to calculate topic distributions of job descriptions and resume and candidate profiles. So using this, we could measure the topic distribution of a job and the topic distribution of a candidate profile or resume, and then calculate how similar they were using cross-entropy laws to determine whether the topic distributions of these were equal. And using this, we were able to correctly identify which candidates were out of our data set. Test data set, we were able to identify which of all the applicants were shortlisted and hired with approximately 76 accuracy by looking at which candidates had a topic distribution most similar to the job description.
Sure. I'll talk about named entity recognition now. Can you go to the next slide? Yeah, so the goal of named entity recognition is you're given a text corpus and you want to find certain type of named entities. And as you can probably presume, one of the main important kind of ideas affiliated with hiring and choosing a candidate is seeing if their skills match the job description. So that was our goal with skills recognition. We wanted to feed in a job description and feed in a resume, and then we can obtain the skills from both of those. So our initial solution to named entity recognition was to use regex matching. So what that means is we get some corpus, we see which words match any type of skills that are in our kind of labeled skills. But this led to a lot of overfitting. We kind of got our model to be more of a regex identifier than an actual machine learning model. So we moved on to a new solution, which was we manually labeled a new data set. And manually labeling allowed us to kind of choose skills that are in the correct context. So can you go to the next slide, please? Yeah, so we were able to get a really nice skill recognition model with 75% accuracy and 70% recall. And what that means is, suppose you're given a job description which has 10 total skills, then our model will be able to effectively identify 7 of those skills. And the missing 25 to 30% is only due to inter-annotator agreement, which is like a couple of our annotators may have labeled skills in a different way. So that's just the kind of human error that's bound. And now we developed a matching algorithm, which given a job description and a resume, we can see how many skills are matching and we can recommend a certain candidate based on that. Next slide, please. Yeah, so now we were able to combine the 3 models that we had, word embeddings, LDA, and NER, and we're able to, like given a certain list of candidates and some job descriptions, we're able to generate the top 20 best matching candidates. And this is like the overarching goal, but the next slide shows some of the other goals that we're able to accomplish, which is during the candidate screening process of hiring, we're able to remove some of the bias since our machine learning model is doing that. We can tune our model so that we foster more diversity in this hiring process, which is a growing thing in today's market. And we're also able to recommend jobs to potential candidates, which is something that's similar to LinkedIn. Or we can also, when an HR specialist is putting a job description out, we can recommend them skills to put in that correspond to that type of job. So that's effectively what we've done throughout the semester. And yeah.
Awesome. Do we have any questions from the audience? We have about 1 minute. Oh, there's one question about how are you nurturing diversity and inclusion practices?
Oh, yeah, so as Sunny mentioned in a previous slide, we're using a lot of different parameters in our machine learning algorithm. So we can train our model to find certain type of people in the job pool, and that's how we kind of foster the kind of diversity that we're trying to find for the role. There isn't like a specific way, but the way we can always potentially tune our machine learning model to be more diverse or more focused on just job matching.
And adding on to that, I feel like at least for as for diversity and inclusion practices, we actually have a lot more work to do, not only in our project, but just in the whole machine learning world in general. So there are a lot of like NLP papers out there about how to learn gender neutral, no biased embeddings, things like that. And this is definitely one of the next directions for the project as well.
Makes sense. Awesome work. I think now that's all the time we have right now. For the Goodly Labs, are we ready to present?
Yeah.
Okay, go ahead.
Sweet. All right. Hey, everyone. We're going to be talking about Public Editor. My name's Eric. I've been on the team for 3.5 years. And Public Editor is a system that uses a community of volunteers and allows them to provide credibility scores for articles. It'll label the problems in the articles. And the process kind of will educate people to train them to identify misinformation for articles that we haven't gotten to yet. So fake news has been a problem forever, but with the internet and social media, there's way more different news outlets now, and we've seen kind of the quality of information go down. So we're hoping to improve that with the system. The way it works is based off of a couple of research papers indicating that first off, pre-bunking misinformation or telling people there might be something wrong before they read the article makes misinformation stick last. We'll expose logical errors in the articles, which can help people be persuaded by our labels more so than just a fact checking would. And we can inoculate readers. So if people have been seeing these labels before, they'll start seeing them on their own, even in articles we haven't labeled yet. NLP doesn't work as well with different contexts, like sarcasm, metaphors. And so the only way to get a high enough traction and training data to this is with Public Editor. This is what the output looks like. It's a labeled and scored article that Andy can tell us more about because he's been working on it.
Hi, I'm Andy. I've been on the team for 1 year, and I've been working on the front end, the visualization part of Public Editor. As you can see on the right, we have a hallmark that when it's not hovered over shows the credibility score of this article as a 93. And when you hover over different sections of the hallmark, it reveals scores for subcategories of errors that Public Editor has identified. Also, when you click on the hallmark, you can scroll to different parts of the article. So it's a tool that allows you to explore the article completely. This is what's being deployed currently at publiceditor.io. And this semester, we've started to add more modes of investigating an article. So you go to the next slide, Eric. You can see the individual contribution mode. This allows a specific volunteer or user, a public editor, to view the highlights and labels that they would have added to the article through their work. And if you go to the next slide, Eric, you can see the article elements mode, which allows you to break down this article into its arguments, its assertions, and its quoted sources, and make it much clearer to see exactly how this article is put together.
Yeah, so my name is Jay. I've been on the public editor team for 4 semesters now, and I'm currently on the user monitoring team. So the scores that Andy just mentioned are created from users independently answering questions about each article, and we call these the consensus answers. So the consensus that all of these users come to, and then we put this on the final product. So for each of the users contributing to this consensus answer, how can we ensure that they're answering truthfully? And as such, how can we reduce the impact of trolls? And our solution to this is to calculate a hidden user reputation score based on how close their answers are to other annotators. And then we can use that to kind of decrease the effectiveness of trolls to kind of game the system. So now users have a score between 0 and 1, and these user reputation scores are taken into account when generating the overall consensus answers. And this kind of creates a feedback loop. So responses from users with a very high score are weighted a lot more heavily, and responses from users with a very low score, very likely to be trolls, are given very little weight. So this prevents these trolls from interfering with the system. And after we generate these consensus answers, that also feeds back into the next time we calculate user reputation scores. So again, that concept of a feedback loop.
Hi, I'm Ewan, and I've been on the public editor team since spring 2019. I've previously been on both the user monitoring and the system validation teams. So what can you do to get involved in the public editor community? There are several ways you can get involved. For instance, you can check out publiceditor.io/try now to try some of the annotation tasks and begin evaluating the articles. You can also help fill the gaps in our mostly volunteer team. We are always looking for software engineers, graphic designers, etc. To build our volunteer team and to build the system. To apply, you can send an email to nick@galileolabs.org. You can also check out our short introductory video or bring a friend to the introductory webinar or follow us on social media. And yeah, that's it for our presentation. Are there any questions?
I'll ask a question. So you talked about how sometimes you can calculate the reliability based on what other annotators were annotating. So what happens when there's very few data points, and how do you kind of figure out their reliability from there?
Yeah, so that's a problem that we have to deal with quite often because we want to make sure that we're using each user to like the maximum efficiency. So we only have a couple of users answer questions about certain articles. And then I think, Eric, could you talk about like IA and how?
Yeah, so we've kind of designed the system so that there's always a minimum number of users that have to be like going and scoring an article for us to like actually be able to use the article. So when we get users, we'll try and put them into like the closest to being finished articles first. So we always will have like the minimum number of users. And so the articles that are almost done get more users before the articles that haven't started yet.
Yeah, and then when we're assigning, when we're assigning these user rep scores, we normally are able to tell if there's one person that really has like quite terrible answers compared to all of the other users. And if there's not, then we can always go back and ask for more data, and then we won't really come to like a solid conclusion if we don't feel like we have enough to base it off of.
Awesome. Any more questions from the audience? Cool. That concludes the 3 presentations that we have. You're free to move around breakout rooms to look at some other presentations if that's still going. Otherwise, I think we would meet back in the main room. And great job, everyone here.
Joanne, I have a request. The first team that went, they seem to have some really great stuff, but some of us missed the first 2 or 3 slides because we were waiting to get into the breakout room. Is it possible for them to show the first 1 or 2 slides of theirs quickly?
Fixing CO2, I still have.
Yeah, I think most of it's still here.
Awesome.
Yeah, we can share our screen.
Yeah, the methods looked super cool. But I was like, wait, what was the fundamental problem here that they're working on?
Sorry, Emily, did you want to walk us through this?
Oh, yeah, sure. Can you go to the next slide? Yeah, so the fundamental problem was that we're working on this project kind of like in conjunction with the Open Catalyst project, which is like a far larger project than what we're doing. We're just participating in it. And then the larger problem is to use AI and try to like search effectively for these new catalysts. And I guess the problem we're trying to solve is like climate change and energy challenges. So we're basically trying to use AI to approximate DFT, which is commonly used for like energy calculations. And we're trying to like use it because DFT is very computationally expensive. We're trying to see if we can find alternative methods that are far quicker and more effective to do more wide range searches for these like new types of catalysts. And then this is just like a explanation of DFT, which is like what people are commonly using now to search for these catalysts. But one of the main disadvantages is that it's like very expensive and it takes like hours or days per relaxation. And then relaxation is also an iterative process. So then you have to do it like many, many times so that the time like builds up.
Thank you very much for showing that. This is about where I came in, and I can ask more questions later, but it's very cool work. All of the projects, really.
Yeah, feel free to ask additional questions for any of the 3 teams. I actually have a question for, I guess, the second team. I guess there's one point when we talk about, is Hireby still here?
Yeah.
So we talked about the mitigating bias, and I was super curious about like what you mean by mitigating bias. Are we talking about like removing some of the bias in the original data, or in part of the feature engineering process, kind of trying to tackle some of that there? Can you go a little bit into details about that?
Yeah, definitely. I think what we mean by remove bias during the recruitment process is like, since we're running our candidates through a machine learning algorithm, it's going to like objectively find who is the most optimal candidate, sort of, and it'll remove the bias and sort of like you choose someone who like you like a bit more, or they meet your kind of criteria a bit more. So it'll be more subjective. It'll be more objective in the way that that optimal candidate matches the job description and all the skills that you're looking for, rather than like something else that might incur more bias of you towards them.
So follow
if that
up.
Makes sense.
So follow up, if I could, Viren. I think some might see that more as replacing a human bias, the bias of some hiring manager, with a different kind of bias, which is, you know, the bias of your first try at the algorithm. The algorithm gets better and better when you learn to like put in features that account for like real human biases that harm people's life chances and their ability to get a job. You're doing such great work. I hope you don't get too excited about this word objective, and you make sure that you know that algorithms have their own biases that they can carry if you're not careful. But,
Yes,
but you're
of
doing
course.
great work.
Yeah, I think you bring up a really good point, and that's why this is not being used for the entire HR pipeline. It's used for mainly candidate screening, and then like we would choose these applicants to conduct like interviews in the process. But definitely, I think what you bring up is really important and we should keep a track on that.
Awesome conversation here. Yeah, good luck to everyone with finals and wrapping everything up. It's a super hectic time, but so glad that we can be here to take stock, as Deborah Nolan said, of some of the successes you've had this semester. And I'll see you in the main room.